We've seen dissociation constant for water in first year was this Kw, right? At 1 atmosphere. Most textbooks now show 2 equations. So yeah, in the old days we used to see this one, the bare proton. Nowadays they're all obsessed with the whole hydronium thing, right? So when you're looking at this, clearly, I mean, it looks a little bit different here. And the fact that we have 2 waters here, how does this play out when we're looking at delta G's, for instance? You know, thermodynamic data. You know how you used to be able to solve for K? And once you had K, you could do that thing where you worked out the concentration of H plus, and that was 10 to the minus 7, right? You've seen this before. So really what you want to do is split your page in half. If you're using this hydronium one, do all this. And if you're using this one, do it. And let's see how it matches up or is kind of the same. So some of this may or may not be in the textbook. So if I put in this, and I guess I could sort of split this, right? And over here we could simply say, what if water decides to just do that? So part 1 said, use delta GFs. You know how the back of the books has those, the standard GF. So you'd almost have to find out what is the Gibbs free energy formation of OH negative. So I looked that up, and it's 157.2. Water was 237.1. I've seen some students look up some different numbers from time to time. This one, it's the same. Is this right? Like, I'm looking at this, it just seems weird. So anyway, if I do this, the delta G naught of this balanced reaction would be 157.2 plus negative 237.1, subtract off 2 times negative 237.1. So you can see how there's 2 of these now. It's going to kill this off, making it 0. You have 1 of them over here. So we get positive 79.9. This one, this is 0 by default. So something's telling me, or 0? So a little bit of question marks about that, but what I looked up was that number. It seems that you would think that this should still be considered 0. But then it won't be correcting for that. So in any event, this one, minus 157.2, minus 237.1. When you do the product, subtract the reactants, you're going to get plus 79.9. Which is the same as it should be, because technically this one's making 1 hydronium and 1 OH negative. Same with this. So thermodynamically the delta G's have to be the same. So if you're asked to calculate K is E to the negative delta G over RT, plug that in here, solve for it, you're going to get K coming out to, put a lot of decimal places in. Obviously, this is KW. So the answer should come out to be very, very close. Now, a lot of students will get things like 9.8 8 or 9.99 or some damn thing times 10 to like the 15, or depending on your decimal places, you could have 1.0001 times 10 to the 14. See how it's a little bit over, a little under? The point is, it's pretty much right on 10 to the 14. So that checks out. So that is all that we're looking for you to compare how this plays out this way. You still get your KW the way that you want. What's next? So calculate. We calculated Q, that's fine. And obviously KW would equal you know, the concentration of OH minus and then the concentration of your H plus thing. So it's like x squared equals 10 to the 14, and you know that x equals 10 to the, well, this is negative. So next up, we have electrochemical data. So how's this going to play out? Well, we would have on this side the electrochemical data. What I would say, I'm still thinking out loud here. You know what's interesting for this is you don't officially electrochemical data. And this is what is just dawning on me. And I think this is part of what this was meant. So let's read this a little closer. You normally don't see too much H3 plus in the electrochemical tables. So number 2 is saying using E naughts, you've got, oh, in other words, if somebody balanced it one way versus another, find KW for 2 electron transfer equation for the version with just 1. So basically what's this time it's asking you, here I'm thinking it's comparing these, no. For electrochemical, it's saying, look at these 2 half reactions. This is just double this. So obviously this has to work out, but you have to prove how it will. So on this half of the page, you have 2H2O plus 2 electrons. Scratch that. 2 H2Os go to 2 H pluses plus 2 OH negatives. What if it was only a single electron transfer? Then you just have 1 H2O. Okay, so when you're using this side, you would have 2H2O plus 2 electrons, H2 plus 2H, and that's negative 0.8281 volts. And then the hydrogen, and that's 0. So you see that this cancels. We're getting what we want, and you get negative 0.8281 volts. Ah, now I see that we're going this. But would this one, it's a 2 electron transfer. This one, you would only have H2O plus 1 electron, half. And then you would have half plus 1 electron. And then you get, you know, your E naught is still going to be, so this cancels. You get that. This one is 2 electron transfer, this is 1. So now what we're supposed to do is calculate K. So we need delta G. So we know that delta G is going to equal negative NFE. So for this one, do you see well, I gotta make sure I'm using my calculator right here. Because this is 2.96485, and then this is 0.8281, that's a negative, and that's joule per coulomb. This says coulomb per mole. So this is coming out to plus 159.8. This one only has one electron transfer, so negative NFE. One electron, so you get 1 mole for this one, so it should be half this number, F times the same E. So this side, balanced this way, has to be half the delta G by default. Delta G, the way we balanced it, yeah, so balancing it, this should be twice the value of delta G as this one. So this will be plus 79.9-ish. So obviously what's interesting here, now I see where this is going. This one, this delta G is double this, so your K value is going to be totally different than this one. So how do we make sense of this? You'll calculate a K from this number and a K from that number. Once you have K, it's not going to look like KW. Well, this one over here will, this one won't. So how do we make sense of this one? You'd have to say, well, we know it comes down to, but do you see the way you've balanced it over here? See your stoichiometric coefficients are 2, that's a 2, and that's a 2. And if they're the same, this one's going to be like solving x to the 4th. So this K, which does not look like KW 10 to the 14th, it's going to be some much bigger number like negative 30 or something like that. No problem, because when you use that K, the way you balanced it, you've got exponents of 2, so it's x to the 4. So when you do this, you're going to come up with numbers where x is approximately 1 times 10 to the minus 7. Checks out. This one already gives you what looks like KW. So this is the comparison of the two ways just on balancing and how that reflects itself in a K that looks like KW. The one that doesn't look like the normal KW, you can break it down into X concentration amounts, which we already know for water. When it does this, it should be 1 times 10 to the minus 7th. So that is the second part of that. And then the last one here says, the third thing, measure and use. So this is simple. This is just basically saying, what if you were to measure the concentrations, calculate KW? Well, you can just do this. If you give me these two concentrations, plug in the numbers you're given, multiply them together experimentally, and just calculate it. So that's part 3, and that does it for question 3.